So I want to go over this question just a little bit more because it's really critical, and there are actually several different ways you can find it, and I've only shown you one so far. So we want the probability that there are at least 3. And I showed you that what that's really talking about is these guys down here, right? All of them. And of course, you could just find all of them and add them up. I mean, nobody's stopping you, right? But it's a little bit easier to find the complement, which is this up here. But wait, there's more. I can actually do this a different way. Let me show you. Than the way I did it. So I could find it by taking binomial dist, and then I say, okay, I want 2 trials because I want to add up 0, 1, and 2, and I want to have it out of 20, 0.05, but instead of saying false like I have up to this point, I'm going to say true. Now notice that gives us the same number we already had. See these two numbers? They're the same. Why is that? Well, you can do it by taking the sum function, which is what we did in the above problem. I'm just going to make this orange for the heck of it. Okay, or I can do it this way, which automatically adds up these 3. It starts at 0, then goes to 1, then goes to 2, and it'll stop when you tell it the number of trials you want it to stop at, which in our case is 2. And then when you're looking for the complement, which is what we actually were in this case, you just take 1 minus that. But wait, there's more. You could have done it all in one step. So you could say, okay, I want you to take 1 minus binomial dist, or binomial.dist if that's the program you have, 2, 20, 0.05, true, and then it finds it all at once. So that's yet another way you could have done it. Or you could have just found each one of them individually like we did here and add them all up. There's another way. So that's 4 different ways that you can find the same probability. Which one you want to use, that's up to you. I'm going to put it right here. Okay. And just for fun, because I know I want to refer to these notes later, I'm going to copy over what I used there. All right, done with that. Next, so the mean and the standard deviation. The mean and the standard deviation are easier to find here than earlier. So let's just remind ourselves, back in section 6.1, we had to go to all this trouble of making a table and then multiplying, and you had to make sure that you used the dollar signs there with the mean and all that jazz. It was also the same thing we did in section 3.3, although it's a little bit easier than section 3.3 because now the probabilities always add up to 1. But what this little blue box is telling us is that there's an easier way. That the mean for a binomial, if it's binomial, will always be n times p. And the standard deviation will always be the square root of n times p times 1 minus p. And I actually wrote them right here. N times p, square root n times p times 1 minus p. So in our case, we want to know how many out of 8,000 births would be twins, knowing that twins happen 2% of the time. So that'd be 8,000 times 0.02. Oops, I forgot to put the time symbol in there. And now for here, square root 8,000 times 0.02 times parentheses 1 minus 0.02, or you could do it in your head, it's 0.98, but close your parentheses, enter. And there we go. We have the mean and the standard deviation all figured out. Now interpret them. All right, this was talking about twins, right? So we expect out of 160 births out of every 8,000 to be twins, give or take 12.52 births. 12.52 sets of twins. So suppose a large metropolitan hospital, they had 200 twins. Is that result unusual? Well, yes, it's past 2 standard deviations. What might be some possible explanations? Well, it's possible this hospital is a center for difficult births or something like that, right? Twins are more difficult, so maybe they help out with that a lot of the time or something.